Hello, welcome. In this session we are going to be looking at proof of divisibility using modular congruence approach. Usually when you have a statement of the form, prove that f of n equals 11 to the n plus 1 plus 12 to the 2n minus 1 is divisible by 133 for all positive integers n. The tendency is always to use proof by mathematical induction. But there is also an exciting way of doing this proof using the modular congruence approach. So in order to do the proof, it is important to first look at the principle behind the proof of divisibility using modular congruence. If there is an integer a and it is congruent to 0 in modulo m, this can only be possible if and only if m divides a. M divides a simply implies that m is a factor of a, or that a is a multiple of m, or that a is divisible by m. When I say that a is congruent to 0 mod m, it is about the fact that when a is divided by m, the remainder is 0. And if the remainder is 0, then it is obvious that a is divisible by m. This is the principle behind the proof of divisibility using modular congruence. Hence, if I have a mathematical statement f of n and I'm supposed to prove that it is divisible by a certain positive integer, an integer greater than or equal to 2 for some natural number n, then it suffices to show that f of n is congruent to 0 in modulo m. To proceed then, there are some congruence properties that we need to recall. The first one is that an integer is always congruent to itself in a particular modulo. The next, or the second one, is that if a is congruent to b, then it is possible to multiply both sides of the congruence by any integer, k for instance, and that if I have a again congruent to b, it is possible to raise both sides of the congruence to a certain power k, where k is a natural number. That if I have two congruences in the same modulo, a congruent to b in modulo m and c congruent to d in modulo m, I can add both congruences or subtract both congruences to have another result. And that finally, a times the inverse of a in modulo m will always be congruent to 1 so long as the GCD of a and m is 1. If the GCD of a and m is not 1, then the multiplicative inverse of a in modulo m does not exist. Okay, now we look at the statement given f of n equals 11 to the n plus 1 plus 12 to the 2n minus 1. For me to be able to prove that f of n is divisible by 133, I need to express f of n as a number in modulo 133. It's only then that I can be able to prove or to make a conclusion that f of n is divisible by 133. To express f of n then as a number in modulo 133, I will express each of the terms that have been summed up to give f of n, each as a number in modulo 133. I start with the first term by writing that 11 is congruent to 11 in modulo 133. That is the first step in building that first term as I'm going to do the proof. In the next step, I will raise both sides of the congruence by some natural number n on both sides of the congruence so that I can be approaching that term that I'm seeking to build up. And the next step, I would have to add 1 to the power of 11, and to add 1 to the power of 11, I simply multiply both sides of the congruence by 11, so that with the laws of indices I can now add the powers on the left hand side to obtain 11 to the n plus 1 congruent to 11 times 11 to the power n. I would allow the left, or rather the right hand side as it is, and then call that congruence the first one. I label it congruence 1. Then I need to build up the second term so as to now add with this one, with the aim of having an expression for f of n in modulo 131. So I bring the second term and start building it up first by squaring 12, and 12 squared is congruent to 144, which in turn is congruent to 11 in modulo 133, because when you divide 144 by 133, the remainder is 11. From there, I need to raise both sides to the power n so that I can build up the first term of that power. And so when I raise both sides to the power n, I get 12 to the 2n is congruent to 11 to the n modulo 133. And the next step will be to raise both sides by a certain number in such a way that I will add -1 to the power of that term. This can only be achieved by multiplying both sides of the congruence by 12 to the -1. And when we do that, you now get on the left hand side the addition of the powers using laws of indices to have 12 to the 2n minus 1, which is the term in its entirety that we are seeking to build up. On the right hand side, we need to express 12. This actually is the multiplicative inverse of 12 to the -1. Actually is the multiplicative inverse of 12 in modulo 133. So I need to find that integer, that if I multiply by 12, it will be congruent to 1 in modulo 133. And to obtain that multiplicative inverse of 12, I will carry out division algorithm of 133 with 12. When I divide 133 by 12, I have 11 and the remainder is 1. And so the reverse Euclidean algorithm expresses the GCD of 133 and 12 as a linear combination of the two numbers. If I now express each term in this expression in modulo 133, I will have that 133 times 1 in modulo 133 will be 0, because it is a multiple of 133, the modulo, and so it's divisible by it, and that means when you divide by 133, the remainder is 0. So the rest of the expression now, we have that 12 times -1 is congruent to 1 in modulo 133. And that simply means that -11 is the multiplicative inverse of 12 in modulo 133. So I can conclude that the multiplicative inverse of 12 in modulo 133 is -11. Bringing the statement, we can now see that the right hand side can be replaced by negative. On the right hand side, the multiplicative inverse of 12 in modulo 133 can be replaced by 11, so that we have this, and this gives the second congruence that is of great importance in the building up of f of n. First congruence that I have built up, I can add the 2, and then my f of n will be obtained. Remember, f of n was 11 to the n plus 1 plus 12 to the 2n minus 1. On the right hand side of the congruence clearly subtracts to give 0, so that we have this statement, and clearly we can see that f of n is congruent to 0 mod 133, which literally means when I divide f of n by 133, the remainder is 0. Hence we can conclude conveniently that the statement f of n is divisible by 133 for all positive integers n. So please, if you did enjoy the video, then subscribe and share so that you can get more exciting videos in the days ahead. some practice exercises. Prove that for all positive integers n, 5 to the n plus 8n plus 3 is divisible by 4, and 2 to the 2n minus 1 plus 3 to the 2n minus 1 is divisible by 5. So you can practice the knowledge with these exercises, and let me see what you have in the comments section. Thank you very much, and see you in the next video.